Okay, so let's start with delta HA. So delta HA is the integral of H1 to whatever the enthalpy of HA is, dH. And previously, we said that this dH can be written like this. Okay? All right. And so in step A is isothermal. And so what that means is that our dt here is equal to 0. And if that's equal to 0, then our CP term just goes away entirely. And so for this reason, because we did this isothermal change in pressure, we actually don't even need to worry about the heat capacity anymore. Okay? And so in the end, our delta HA just simplifies down to this. Okay. Right, where I want to point out, now instead of a second derivative, we're only dealing with a first derivative, which produces significantly less error than a second derivative does. Okay? Alright, so that was the calculation for HA. Let's now move on to calculating HB. So I'll go to the next page. Okay. Delta HB, the setup is the same, except now we're going from what I call HA to HB. The dH still described initially by the same equation. Okay. Right, but this time what we're doing is we're changing temperature but holding pressure constant. And so that means our dP term is going to be equal to 0. And so as a result, we don't need to worry about this big chunk of a term at all. Okay? So that's isobaric. And so what we're left with is that delta HB is equal to, I'll still keep the pressures in here for now, essentially we just need to worry about this heat capacity term. Okay? Generally, remember the heat capacity can be expressed like this, where we have a ideal gas term and then another term that accounts for non-idealities that are affected by pressure. Alright, this is where that second derivative was. And the dt is outside. Okay? Alright, so at first glance this looks still kind of nasty. But once again, in this hypothetical process path, in this step B, we're doing it isobarically. So dP is still 0. So that goes away. And so what we're left with is that our delta HB is just the integral of the ideal gas heat capacity with respect to temperature. Alright, so here we're only dealing with the ideal gas heat capacity. You don't need to worry about this kind of nasty pressure dependence for the heat capacity. Okay? Alright, so that was delta HB. For delta HC, there we're changing the pressure isothermally. And so the form of the equation ends up being almost the same as the form for step A. The only difference is the bounds of the integral. Now we're going from that pressure B to the final pressure P2. Okay? All right, and so if we take all these things together, so H2 minus H1, right, and let's plug in for HA, HB, and HC. So for HA, we're going from pressure 1 to 0 pressure. For HB, we're changing the temperature of the ideal gas and then for HC, we're going from 0 pressure to P2. Okay? All right, now some things I want to point out to, it still kind of looks like a long equation, but I want to point out some things to you that might make, this a little bit more clear about why this is useful. So I mentioned here that we're only dealing with the ideal gas, right? And so, to be more precise, here, this middle term, we could think of it as the difference in enthalpies between the outlet and the inlet for the ideal gas versions of them. Okay? And so what I'm going to do is, for demonstration purposes, I'm going to move this to the left-hand side for a bit. And so what we'll have on the left-hand side is our real H2 minus our real H1, put that in parentheses, and then that difference, we're going to subtract off of it the difference between the ideal gas versions of H2 and H1. Okay? So on the right-hand side, what we're left with, I'm going to kind of rearrange this a bit, is I'm going to write the delta HC term first. And then I'm going to write the delta HA term second, but I'm going to write the negative of it. And all that changes is the direction of the bounds. And so here we were going from P1 to 0, but for the negative of it, we're going to go from 0 to P1. Okay? All right. And so the reason why I rearranged this equation in this manner is right here, this is the actual difference between the outlet enthalpy and the inlet enthalpy that we want. I'm subtracting off of it the contributions that come from the differences in the ideal gases, right? That's what H2 Ig minus H1 Ig is. And so what we're left with on the right-hand side, if we subtract off the ideal gas contributions, what we're left with here are the non-ideal gas contributions. Specifically, this first term that we have here, this accounts for the non-idealities of our outlet stream's enthalpy. And this term right here, it also accounts for the non-idealities, but for H1. Okay? And so, these terms describe how, these streams actually depart from ideal gas behavior, right? And so what I'm going to call these terms is I'm going to call these departure functions, right? And they're departing. The departure here means that we're departing from ideal gas conditions. Okay? And so to generalize the departure function, I'm going to call it, for whether it's your outlet or your inlet, the departure function, its mathematical form is going to have this structure, where you go from 0 pressure to whatever pressure your stream is actually at. That's going to look like this. Okay? Where once again, there's no second derivatives here. We just have a first derivative. And for that first derivative and for the volume term here, what you could do is you could plug in an equation of state there to get like an actual function that you could use. Okay? All right, so that's what the definition of a departure function is. And so going back to just looking at h2 minus h1, what that is going to be equal to is it's going to be equal to the sum, or the difference between the differences of the ideal gas streams. I guess this is a sum. And then we're going to add onto that the differences between the departure functions. Okay? Or once again, the first term accounts for changes between ideal gases, and the second term accounts for non-idealities.